I'm going to simulate a random walk. Okay? Now, the idea behind a random walk is you start with some initial step, and whatever next step you are going to be at is based on previous step with a bit of noise added to it. So, what kind of letter should we use? X is fine. Okay. X, let's say I'm starting with 2, some random value. Doesn't have to, oh, we can start at 0. Why not? And I'm going to move forward, backward. That was our case. How many time steps should we go? 10. We'll start with 10. Number of time steps. And each step will depend on the previous value. So x of t will depend on x of t minus 1. Some programming languages, or some people do it as t plus 1 equals xt. Doesn't matter. We're all talking about the same thing. Think of changing the summation index. Are we done yet? What am I missing?
The noise.
The noise. So I'll call it epsilon. Should I keep track of that? No. Random. So epsilon, typical noise is Gaussian, so R naught. One random value. You are at 0. Couple of things could happen. Drunken talk, random walk. Either you make a positive step, or you go backward. So one of these 2 things could happen. So I'm going to center it as a bell curve, and you can go 3 steps, any value from 0 to 3 steps forward, 3 steps backward. Good. So hence mean 0, standard deviation 1. So 0, 1. That should do. I have a random walk generated by them. We want to see this. So plot time series, time on the x-axis. So t, comma, the value of x. I hope you know the difference between teal and turquoise. Oh, do we know? Yeah, teal's better, right? Okay, ready? I can also add a line at 0. That is your starting point. So let's add a horizontal line. 0. 5. Okay, lovely. Okay. That is my random walk. Seems like I'm making progress, right? Lots of positive steps. Now, if I run it one more time, are we going to get the same picture? No. Completely different. This is something that we do in research, setting a random seed. Nothing in life is purely random. Things are pseudo-random. So if I do something and I want someone else to get the exact same result, in other words, in this computer, I generate a series, go to a different computer, generate a series. I want them to be the same because we want to see the seed, when you set it, everyone will get the same picture. So first time I run it, that's what I get. One more time, stays the same. Good. Still random, but I'm setting the seed so that when you go back home and run this, you get the exact same picture. How do you get a different walk? You just change the seed to a different number. Okay. The epsilon would be the random Gaussian or white noise that I'm adding. And that is my simple model. And we don't want to observe just 10 steps in business and econometrics and all those fields. We don't make assessments based on just 10 time steps. Business, finance, right? Did you take econometrics? If you are observing, say, S&P 500, you just look at the last 10 days, or you look at a span, really long span, but you go all the way back. So I need more time steps. So let's
Yeah, we should have learned econometrics or they taught us in data. Not good.
At least it's not as bad as Excel. I'm not Excel's starters. Even I don't use
Jesse, right?
I'm an hour Python
Jesse, right?
Okay.
Yeah.
So I have it in points. That's why it's such a bit messy.
Yeah.
Let's turn it into a line. It's prettier. Okay. That is a random walk. Yes. So person starts somewhere here, sort of made progress, 25 steps, all of a sudden back to where they started, drunk person. But about that initial value, yes, is it possible to go below the initial value? Absolutely, it's possible. Looking at this picture though, I can say that this is not stationary. Agree? Condition for stationary is you could have variability. Variability is important in statistics, but whatever wiggles and wobbles that I see has to be about some level. Like here's all over the place. Non-stationary. There are other processes, one of them is called Unstein-Uhlenbeck process that is also non-stationary. It's going to look weird, but we can't model things like this as well. Econometrics, they probably did it. What is that word that you use in econometrics in terms of market fluctuations? Or what did you use?
I mean, we just use like variability,
Yeah, and there's a different word for it. Starts with V.
variance,
What? The second letter is O.
volatility.
Volatility, right? That's fluctuation in the market. I say tomato, you say tomato, we're talking about the same thing. There are uncertainty, volatility in the market, same thing. Extremely volatile here. So we can generate a random walk easily. I am going to get into this today. One of the key things in time series is autocorrelation. Right. Or easily gives us autocorrelation. So I'm just going to put ACF of X and plot road type H. I'm going to use a fancy word. And wow, these would be autocorrelation. In regression, when you find a correlation coefficient, what does it tell you?
How much one variable depends on another.
How much one depends on another. So let's say you fit y equals mx plus b, and you get some value for m, some value for b using your data. If the correlation coefficient ends up being 0.999, then we can say that there is a strong relationship between y and x. If it is 0.1, well, useless model, you can't use it for prediction. Same logic. Instead of correlation coefficient, which is a single number, we have a correlation function. The reason being, can someone guess? So linear regression, one coefficient to measure correlation. Here we have a function. Any thoughts as to what? Think of an auto-regressive model. Auto-regressive.
There would be like a correlation coefficient for each like step.
Very good. There will be a correlation coefficient, a correlation value for each step. In other words, if whatever decision that I make today is based on yesterday, and if it is something that I take very seriously, I am heavily correlated between today and yesterday. Do you agree? And if someone bases whatever that they're going to decide today or yesterday and the day before, I should see a good amount of correlation between today and yesterday, today and the day before. But you can't go from here all the way to the day before. Rather, you can compare yesterday to the day before. Those two are correlated.
So there's not like, we have 3 days, right? Day 1, 2, and 3. So there wouldn't be a coefficient for day 1, 2, 3. It would have to be to 2 and then from 2 to 3. If I'm understanding you right?
So, do I have to look today and connect it directly to, say, 3 days prior? Is that what you're asking?
Mhm.
You can't do it. It's an ethereal-based serial autocorrelation. There is a reason as to why that will tie in with strict sense stationarity. So do you understand the concept of correlation? So in typical linear regression, we have one number that tells us how strong of a correlation we have. Here, we are trying to see how we are correlated to past time instances. So we've got to measure correlation at each time step. Okay. Ready? Before I hit on, what do you expect to see? Do you expect to see a nice little pattern between today and yesterday? Or current time step and the previous time step? Not really? Okay. I'm going to say the same thing.
Will the column chart, is that gonna measure the correlation, like for each step? I mean, it's not gonna show, but like, as it's gonna show like each timestamp and the amount of correlation it has?
Yes.
Okay, so I would imagine as you go farther back, there'd be less correlation.
But do you expect a nice little thing or all over the place?
Probably all over the place.
It's probably going to be all over the place because, I don't know, I look at this picture, I don't think things are properly connected to the previous values all over the place. So, hit run, see what happens. There is a picture. What was a correlation function? Something like this, very difficult to move. One name around the world, not that great. There are some non-stationary processes, will have a pattern of this sort, but you can't model under certain conditions. This will take a very slow lag, probably 100 steps, 200 steps back in time. So if you are correlating time step 0 with time step 0, what do you expect the correlation to be? 100%. It's right over here. Time step 0 to time step 1. Right? Time step 1 to 2. Slowly decaying. Eventually, it is going to become 0. In this case, it's not going to. Another process called long memory process would follow a similar ACF path. So just like how you would obtain a scatter plot prior to doing regression analysis, you would come up, you would start here to identify your model. Good? Great. Going to make a slight change to our expression and throw in thing. And I'll put that note there. So a random walk value of phi has to be 1. That's where I started. It is simply an autoregressive model as order value 1. Give me a number between 0 and 1.
0.22.
0.22. Okay. So step t is connected to step t minus 1. The value of phi is 0.22. So do you think that there is a strong connection between xt and xt minus 1? No, it can't be, right? What about xt and xt minus 2? If it is an AR1 mode, it's probably going to be less. Let's see what happens. So, on this first picture, oops, okay. stationary? No. I expect to have noise, but is it wiggling in a balanced way about the center?
Honestly, yeah.
Center on line.
About the center compared to the previous picture? I had a level. Level was 0, that was my initial state. It wasn't a balanced curve, it was all over the place. But over here, I have level 0, but whatever noise that's getting added, it's getting added in a balanced way. Why am I getting such a messy picture? Because the way you are correlated to previous values is very small. Hence, patterns not that great. If you look at the autocorrelation function, or plot will automatically, that is fine, color is one. XT correlated to itself. XT correlated one step backwards, expected to be high. But if it is an AR1 model, it can only depend on the previous time steps. So if you go 2 steps out, not that significant. You go all the way back, not that significant.
So is phi psi in our,
Yes,
okay.
Does psi always have to be between 0 and 1 no matter what the order is, or can that change?
it has to be this way.
Okay.
For AR. Reasons, we will get into it. Omar said, oh, that looks pretty messy. Reason being, 0.22. Give me a number between 0.7 and 1. 0.9. Good. If you observe this pattern, it is starting to look pretty much like where we started. 1 to 4. 0.9 is close to 1. Hence this non-memory kind of state that's happening. So we are approaching a random walk. Look at that picture, it's getting there. It's wiggling back and forth, not as bad as phi equals 1, or psi equals 1, but still too much variability. Give me a number between 0.4 and 0.6. Don't give me a 0.5. 0.4%. I'll let you talk for it. I like nonsense too. The powers so I have that still noisy looking 0.48. That is my ACF plot. I'm still getting some random stuff. What this tells me is for the observed series or whatever that I simulated, I can actually go past, just 1 step. I can go 2 more steps. Gets into model selection in the semester business. I want you to look at this picture carefully. Yes, if you moment, glance, look. So 0.48. Prior to that, we used 0.9. Aaron gave us 0.9. Look at that carefully. Good. Prior to that, which is 0.2.
0.22.
0.22. Look at that carefully. Do you see the pattern? Ellen?
The lower that fee is, the more like stationary it is. Like it's like less ACF.
It's getting closer to, a typical AR1 case. Okay, one observation, what is another? I'll give you a hint. there is a connection between this picture and the sun.
Greater that fear side is, like, the stronger the autocorrelation.
True. Absolutely correct. Perhaps I will paraphrase. Do you see the value of phi that I started with in this picture? Emily, right? Aaron. Aaron,
The
okay.
immediate next step is the, like, yes.
The very next step, very first problem that I found, simulation, it was pointed to right there. And the next value we picked was 0.9, it's right there. The next value we picked was 0.48, right there. So if you are going to look at an AR1 model, you can just look at the p value, the first step, and stop. That's it. But life is not that easy. You can't model everything in life using an AR1. Good.
How does the program R know that it's an AR1 model, that's only order 1?
Great question. Or doesn't know. I know that it is AR1, right?
Yeah.
In practice, let's say you get a data set that looks something like that. But you're observing something, that's what you see. What I would do, what you should do, is get an ACF and ask yourself, should I fit an AR1? Should I fit an AR2? Should I fit an AR3? Now, from experience, I look at this, I could go all the way up to AR3. The reason being, those three values are above that blue line, above that white noise limit. So whatever I'm observing in the series has meaning up to 3 steps in the past. So I can go all the way up to AR3 in this picture, or use an AR2, or use an AR1. Goes back to what I mentioned in regression analysis, applied science, the principle of parsimony. If you can't explain something, in just 2 steps, and if you want to explain something using 100 steps in the past, which one should you pick? If both of them are performing the same way? 2 steps, right? If someone can't explain whatever actions that I would take today based on just yesterday, and it is a good prediction, why bother going past that? So in practice, I will start with an AR3, I'll fit an AR2, I'll fit an AR1. I'll compare the models and pick the one that works best. Good, that's pretty much how we do it. Are we clear? So, AR1, easy to get the coefficients, not so much with other cases. So that is the simulation. And